Hi, this is Dr. Mead. This is biochemistry. This is AP Bio, biochemistry review, part 1. Try to make them short and sweet so that the videos load quickly. Whee! Bear with my terrible handwriting because I'm not used to doing this. Okay. Oh, slide 2. Come on. Slide 2. I'm telling you. Slide 2. Slide 2. Slide 2. Make it happen. No. Okay. Pause. Okay. Now that I got that done, you should know the basics. If you remember, we're talking about knowing things you gotta know, not because they're gonna ask you specific questions, but because if you don't know them, it's hard to explain other things. So you should know the properties of water. And by that I mean that water is highly polar, that it's the universal solvent, high heat of vaporization. Whoa, that's a good one. I'm just kind of taking a shorthand because there's stuff I'm going to draw, which is why I decided to go this route. Cohesion and adhesion, and high specific heat, so ice floats. Okay, so you could see why okay. A big question might be to explain something about where did that big arrow come from? I don't know. Okay, I have a big arrow. That's kind of cool. Don't know what that's for. Not my intention. Back to that. Okay, why is life on Earth dependent on the properties of water? And you probably have noticed that in the news when they are talking about, for example, the Mars rover mission, that everything they look about with Mars is to find water and evidence of water in the past and the present. They find salt crystals. They get excited about the idea of water. They find something that looks like water might have run through previous rivers. They get excited because water indicates the possibility of life. So why is life on Earth dependent on the properties of water? So that's one of those big picture questions that shows evidence of everything you could have understood about AP Bio. So why does the polarity of the molecule little Mickey Mouse thing. I could be like getting fancy with colors and stuff, but this is iPad thing is new to me, and this program is new to me. So why does the polarity of a molecule have to do with life on the planet? And it really does kind of all come down to that. This is why ice floats. This is why water has a high specific heat. This is why it has a high heat of vaporization. All comes down to this magnetic, this polarity aspect of water. So if you could review that, practice explaining out loud, record yourself on your phone and listen to it. Do you make any sense when you explain water as a polar molecule and why life exists because of it? Okay, so let's talk about pH for a second, because this is one of those things that I think could get us into a little trouble when we kind of think about the area of kind of math and graphs and stuff like that. So we know that it's a scale, and we're talking about water still. pH, we're talking about liquids. We're talking about molarity, and I'll do a little piece on molarity on the next one. So first of all, we're basing this on this idea that 7.0 is equal to pure water, and at that point, what does that mean? To be neutral means something about water. We'll come to that first in a second. And so the scale is going from 0 up to 14, and 7 being in the middle. And if you're down here, you're what? And if you're up here, you're what? Well, you're an acid down here, and you're a base over here. And that part we all seem to be pretty good at. And the part that's kind of tricky to understand is that the leap from 7 to, say, 8 is ginormous, because we're talking about a logarithmic scale. Okay, and not only a negative logarithmic scale. And so that tends to be a little bit tricky to understand. So if you have a pH of 3, then you have 1 times 10 to the minus 3, or 0.001 moles per liter of hydrogen ions in solution. Okay? In solution. Okay? Because we're talking about a liquid here. Okay? While if we are talking about... Well, so let me ask the question then. So what would it be to be a pH of 4 then? How different is it to be a pH of 4? So if you can figure that out for a second before I go to the next slide, pause for a second, because that would be a common question to ask you how different it is to go from a pH of 3 to a pH of 4, and ask you what that difference is in numbers, okay? So just keep this in mind for a second. So a pH of 3 is 1 times 10 to the minus 3, or 0.001 moles per liter hydrogen ions in solution. Okay, so pH is about hydrogen ions. All right, so next. Okay, so if pH of 4 is 1 times 10 to the minus 4, or 0.0001 moles per liter of hydrogen ions in solution. Okay, so therefore a solution of pH of 3 is 10 times more acidic. Well, that's terrible acidic than the pH of 4. Okay? And so if we were to compare a pH of 6 to a pH of 9, and I want to know how much more acidic is a pH of 6 than a pH of 9 and wanted you to tell me, how would you figure that out? Pause, pause, pause. And of course, the answer is then 1,000 times more acidic. Okay, so it's not 3, because if I can draw you a little chart to help you study this for a second, I can draw you a little messy chart to help you study this for a second. Not so great with the stylus here, but getting there. So if 1 is 10 to the minus 1, our 0.1 molar, and then a pH of 2 is 10 to the minus 2, and 0.01 molar solution, and 3 is 10 to the minus 3, or 0.001 molar solution, and 4 is 10 to the minus 4, or 0.001 molar solution, and then ... 7, okay, 10 to the minus 7. In front of all these obviously is a 1 times, that's technically the way you write those things when we're talking about moles, dating you back to your algebra there in chemistry. How many zeros would we have here? Well, 7. Hello, of course. When we have a little 7 there, that's the hint. So 1, 2, 3. I mean, 7 places in the decimal, not 7 zeros, excuse me. Oh, it's a long day. Sorry, 7 places. So 6 zeros and 7 places. Oh, I just really threw you off. I wish I could know how to rewind and not sound stupid there, but there's my little mistake. So if I could, I would rewind and go back in time right now, because somebody invented a time machine, but they didn't, and say that, this is the cheesy way that I learned it. And I'll show you my little cheesy trick. In fact, I'll even change colors, because at least I know how to do that. To count my little decimal places, I would go 1, 2, 3, 4, 5, 6, 7. Okay? So that's how I learned to count decimal places, because sometimes they get really, really big. Like pH of, 13, which is 1 times 10 to the minus 13. And then if I had to really draw that, this is how I would do it, and then I would erase it. So I'll make it red for you. Oops. So I would take my little red one. Go away. And I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then I fill them all in with zeros except for the last one. This is little baby math, but I know some of you did not have awesome time with math. So there you have it, folks. Molar solution. Okay, so there's the basics of pH in 3 minutes. Okay, so that's the pH part, but now let's talk about pH and pOH. Alright, so here's H2O, and all the time there's a little bit of dissociation going on where we have some high hydrogen ions and some hydroxide ions going on. So when we talk about pH, the other big piece to consider, and you can read all about this in, if I had to guess, I think it's chapter 3-ish. Anyway, when we're adding up those numbers and thinking about 0, 7, and 14 and all that stuff, we use this symbol to mean concentration. Hydrogen ions and OH, hydroxide, equal 14. So together, we're going to have the total of 14. So hydroxide ions and hydrogen ions together are going to be 14. So if we know that we have a pH of 3, because I told you that pH of something equals 3, and I say, hey, what's the pOH of that thing, then it's very easy to figure out. What is it? It's 11, because it's super simple. It's just 14 minus 3 equals 11. It's as simple as that. Okay? So that's all there is to combining that stuff. I think that's really all I wanted to say. The last piece to remember is buffers. So, and then I'll end this one so it's a nice short video, although now it thinks it's 2 minutes long. I thought I had 8 slides going, so I'm really confused. Anyway. Okay. Oh, each slide is another minute. Okay, anyway, buffers. Buffers. Okay. Contribute to homeostasis by accepting or donating as needed. And I'm not going to go through it more than that. That's the big picture. The little picture about it, I really suggest you look up. The most important buffer in human blood is the bicarbonate ion, and that's the one we used in our little paper example. So that's the end of the water piece and the introduction to biochemistry. The next one will be about carbon compounds, and I don't think this worked as one whole video, but I'm going to try it and see what happened.